the power plants that kept Britain's war industry alive. January 15, 1940. Central Electricity Board Headquarters, Trafalgar Buildings, Charing Cross, London. Sir Archibald Page, chairman of the Central Electricity Board, stared at demand projections that seemed impossible. The Ministry of Supply was requesting electrical capacity for 300,000 munitions workers who would be hired in the next 18 months. Shadow factories converting motor plants to aircraft production needed power equivalent to small cities. Royal Ordnance factories filling artillery shells required uninterrupted electricity 24 hours daily. The grid was already operating near maximum capacity, and German bombers had just begun reconnaissance flights over British power stations. Page's handwritten note to the electricity commissioners, dated that afternoon, contained a single underlined sentence. If we fail to deliver power, the war is lost before a single German soldier sets foot on British soil. He was right, but he had no idea just how close to failure Britain would come. Before September 1939, most Britons took electricity for granted. Flip a switch, lights appeared. Simple, invisible, routine. What they didn't understand was that their electrical system had been, until very recently, a chaotic disaster. In 1920, Britain had over 600 different electricity companies operating independently. Some supplied alternating current at 50 Hz. Others used 25 Hz, 60 Hz, or 100 Hz. Entire neighborhoods operated on direct current with no way to connect to adjacent areas using AC. Voltages varied wildly, some areas at 200 volts, others at 240, still others at obsolete standards. A factory in Manchester couldn't simply import equipment from Birmingham because the electrical standards were incompatible. The fragmentation was strangling British industry. In 1925, Lord Weir investigated, and his assessment was brutal. Of 438 generating stations owned by authorized undertakings, fewer than 50 were efficiently sized. Standby capacity averaged 80%, meaning 4/5 of reserve equipment sat idle, wasting capital. Load factors were unreasonably low because stations couldn't share power during peak demand. The diagnosis was clear. Britain needed a national gridiron linking efficient stations across standardized transmission lines. The Electricity Supply Act of 1926 created the Central Electricity Board with exactly that mandate. Sir Andrew Duncan became the first chairman. A Scottish businessman from Irvine, Duncan had transformed the coal industry as coal controller after World War I. His appointment to the CEB in 1927 gave him an even more ambitious task: build Britain's first national synchronized electrical grid from scratch. Make it operational before the next war, because everyone knew another war was coming. Duncan assembled a team that combined industrial pragmatism with engineering brilliance. John Brooke, former permanent secretary at the Ministry of Transport, became CEB secretary despite taking a pay increase that raised eyebrows. David Coates, a practicing accountant with business experience, took charge of finances. Johnstone Wright, deputy chief engineer and later chief engineer, handled the technical architecture. Their timeline was aggressive. Construction began in 1927. The first grid tower was erected near Edinburgh on July 14, 1928. By September 1933, 6 years ahead of many predictions, the grid was operational as a series of regional networks. 4,000 miles of transmission lines, mostly overhead cables, connected the 122 most efficient power stations. Operating voltage, 132 kilovolts. Frequency, standardized to 50 Hz throughout, but regional grids weren't enough. True national integration required all regions to operate in parallel synchronization. That happened almost by accident. On October 29, 1937, night shift engineers, without authorization, briefly synchronized all regional grids to test if it would work. It did. By 1938, Britain's national grid operated as a fully integrated national system. The timing was extraordinary. War began September 3, 1939. Britain's grid had been nationally operational for just 14 months. 14 months that would determine whether Britain could fight at all. The physics of electrical grids are unforgiving. Alternating current at 50 Hz means the current direction reverses 100 times per second. Every generator on the grid must remain precisely synchronized. A generator running even slightly fast or slow creates phase mismatch, potentially cascading into regional blackouts. Grid engineers in 1939 managed this synchronization manually. They monitored massive analog control panels showing real-time load demand across regions. They calculated which power stations to activate based on coal availability, maintenance schedules, and geographic distribution. They forecasted demand hours in advance because coal-fired stations took time to bring online. One miscalculation meant blackouts. Blackouts meant factories stopped. Production delays meant fewer aircraft, tanks, and shells. Fewer weapons meant more British soldiers died. The pressure was immense. When war began, the CEB controlled 171 generating stations across England and Wales. These ranged from massive urban stations like Battersea Power Station, producing 1/5 of London's electricity, to smaller regional facilities. Most burned coal. Many were aging infrastructure originally built for local service, not national-scale industrial warfare. The challenge facing Sir Archibald Page and the CEB in early 1940 was unprecedented. Britain needed to triple munitions production. Shadow factories were converting peacetime motor plants to build aircraft, requiring massive electrical installations. Royal Ordnance factories were multiplying across the country. ROF Chorley in Lancashire employed 26,000 workers filling artillery shells and bombs. ROF Bridgend in Wales handled propellant production for 40,000 workers at peak capacity. ROF Swinnerton in Staffordshire became Britain's largest explosives facility. Each factory consumed electricity equivalent to a medium-sized city, and they all needed uninterrupted power. A 5-minute outage could ruin an entire batch of explosive compounds, wasting thousands of pounds and days of production. Worse, unexpected power fluctuations could trigger accidental detonations. Simultaneously, aircraft production was expanding exponentially. The Shadow Factory scheme, developed by Sir Kingsley Wood and headed by Herbert Austin, brought motor manufacturers into aircraft production. The London Aircraft Production Group at peak employed 51,000 workers across 41 factories. They produced one Halifax bomber every hour, for years. That required electrical power beyond anything Britain had previously supplied. The CEB's solution was aggressive expansion. In 1940, the Electricity Commissioners, in agreement with the Central Electricity Board, proposed installing 180 megawatts of new generating capacity. 4 existing stations would be expanded. 2 entirely new stations would be built from scratch, one at Early, east of Reading, another at Castle Meads, Gloucester. Early Power Station became the only power station directly owned by the Central Electricity Board. Construction began in January 1941. The station would house a Parsons 40-megawatt steam turbo alternator, 3 boilers with combined steam capacity of 600,000 pounds per hour at 635 psi at 850 degrees Fahrenheit. The engineering was cutting edge for 1941, but construction happened during the Blitz. German bombers were attacking industrial targets nightly. Power stations were obvious priorities. Early's construction site had no special protection. Workers built the station, knowing Luftwaffe reconnaissance flights tracked their progress. The timeline was brutal. 22 months from groundbreaking to operation. Most peacetime power stations took 4 years to build. This was wartime. Delays meant soldiers died. On December 8, 1942, Early Power Station came online. The 40-megawatt turbine began feeding the grid. It was operated by Edmondson's Electricity Corporation under contract until nationalization in 1948. But Early was just one station. The real story of Britain's electrical survival wasn't new construction. It was the interconnected grid's resilience under sustained bombing. September 7, 1940, the Blitz began. Over 350 German bombers attacked London in the first raid. 300 tons of explosives fell on the docks and surrounding areas. Among the targets, power stations. Battersea Power Station, visible for miles with its 4 iconic chimneys, seemed an obvious target. The station produced 1/5 of London's electricity. Its Art Deco brick structure dominated the south bank of the Thames. American observer Ralph Ingersoll, watching the bombing, wrote that Battersea received only a minor hit despite being one of London's largest landmarks. This wasn't mercy. It was navigational necessity. RAF pilots used the white vapor plumes from Battersea's chimneys to navigate home through fog and smoke. The Luftwaffe used the same plumes. Destroying Battersea would eliminate a navigational reference both sides depended on. But the reprieve was partial. On September 8, 1940, the day after the first Blitz raid, both Battersea and West Ham Power Station were shut down. The Luftwaffe had hit surrounding infrastructure, severing transmission connections. In November 1940, an unused extension of Battersea was hit and destroyed. But the main station never went offline permanently. This was where the interconnected grid proved its value. When Battersea went offline temporarily, power from stations in South Wales flowed through the grid to compensate. Generators in the Midlands ramped up output. Emergency connections between regions, built as backups but rarely used before the war, suddenly became primary transmission routes. The grid's redundancy meant no single bombing raid could cripple Britain's electrical supply. Consider the alternative. Under the pre-1926 system of isolated local grids, destroying Battersea would have blacked out 1/5 of London indefinitely. Factories would have stopped. The underground rail system would have failed. Critical war production in London would have ceased until Battersea was rebuilt, a process taking months or years. Instead, London's factories experienced temporary voltage reductions and rolling brownouts, but never complete extended blackouts. Production continued. The Luftwaffe didn't understand why their strategy was failing. German intelligence reports from late 1940 show confusion about why British industrial production wasn't collapsing despite documented bomb damage to power stations. They didn't grasp that Britain's integrated grid could reroute power faster than German bombers could destroy individual stations. Power station workers became unsung heroes of the Blitz. They worked 12-hour shifts, 7 days a week. When air raid sirens sounded, protocol dictated workers should evacuate to shelters. Power station crews stayed. Someone had to monitor the turbines. Someone had to adjust coal feed rates. Someone had to manage grid synchronization during fluctuating demand. If the workers left, the grid failed. If the grid failed, Britain lost. So they stayed. Thomas Alderton, a turbine operator at Fulham Power Station, kept a diary during the Blitz. His entry for November 17, 1940 read, "Bombs fell within 200 yards tonight. Shrapnel hit the cooling tower. We kept the turbines running, adjusted output to compensate for Battersea being offline, home at 7 a.m., too tired to eat." Alderton died in 1943 when a V-1 flying bomb hit his home in Chelsea. He was 34 years old. He had worked 1,027 consecutive days without missing a shift. The grid's wartime challenge wasn't just bomb damage. It was coordinating wildly fluctuating demand across unprecedented industrial mobilization. Aircraft factories operated around the clock, but their power consumption varied dramatically depending on production stage. Sheet metal stamping presses drew massive current in brief bursts. Rivet guns created power spikes across entire factory wings. Paint booth ventilation systems ran continuously. Final assembly areas needed bright lighting but minimal heavy equipment. Multiply this complexity across hundreds of factories. Add munitions plants with explosive mixing equipment that couldn't tolerate voltage fluctuations. Add shipyards with heavy cranes drawing enormous intermittent loads. Add the civilian population's domestic demand, which spiked during evening hours. Grid engineers had to predict and balance these demands in real time using 1940s technology. No computers, no automated load balancing, just engineers with slide rules, demand charts, and telephones coordinating between regional control centers. The National Control Center, later based in Bankside House from 1962, didn't exist in 1940. Instead, area control centers in Newcastle, Leeds, Manchester, Nottingham, Birmingham, St Albans, East Grinstead and Bristol coordinated independently. Engineers telephoned each other to arrange inter-regional power transfers. Birmingham Control to Manchester Control, can you take 20 megawatts off our grid for 3 hours? We're bringing Hams Hall Station offline for emergency repairs. Manchester confirms, we'll activate Barton Station to compensate. These conversations happen dozens of times daily. One mistake meant cascading blackouts. Consider a specific example from March 1941. The Royal Ordnance Factory at Chorley, Lancashire, notified the grid that they needed to run explosive mixing equipment continuously for 36 hours. This required uninterrupted power at precise voltage. Any fluctuation could cause the nitrocellulose compound to become unstable. Simultaneously, the Vickers Supermarine factory in Southampton was completing a production run of 127 Spitfires that required round-the-clock assembly work. And the Port of Liverpool was unloading American Lend-Lease equipment using electrically powered cranes operating 20 hours daily. 3 massive simultaneous demands on the grid. Grid engineers calculated available capacity. They determined that Manchester area generators could cover Chorley's needs. Southern stations would supply Southampton. Liverpool required activating 2 reserve stations in Wales. Then German bombers hit Liverpool on the night of March 12, 1941. The Liverpool Blitz. Docks were burning, power lines were severed. Liverpool's demand suddenly dropped because factories were evacuating workers. But that sudden drop in demand risked oversupplying other regions, potentially overloading generators. Grid engineers in Manchester and Bristol made real-time adjustments. They throttled back generators. They rerouted excess capacity to Chorley and Southampton. They maintained grid stability despite chaos in Liverpool. The munitions mixing at Chorley continued without voltage fluctuation. The Spitfires were completed on schedule. Liverpool's power was restored within 18 hours. This happened hundreds of times during the war. Invisible coordination, unsung heroism, technical excellence under pressure. The grid's greatest challenge wasn't bombs. It was coal. Britain's electrical grid in 1940 was entirely coal-dependent. Every power station burned coal to create steam to spin turbines. No coal meant no electricity. No electricity meant no war production. But coal miners were being conscripted for military service. Production dropped. Transportation infrastructure was bombed, limiting coal distribution. Prices doubled between 1939 and 1941. Factories that had operated private generators before the war faced even worse shortages. They abandoned private generation and connected to the national grid. increasing demand precisely when coal was scarce. The government implemented coal rationing. Power stations received priority allocation, but supplies ran dangerously low multiple times. The winter of 1946–1947, after the war, nearly broke the system. Severe gales and a brutal freeze paralyzed transportation. Coal stocks at power stations dropped to critically low levels. Newspaper headlines warned, electricity services in danger, stocks critically low, coal embargo on ships leaving Britain. For the first time, the grid couldn't meet demand. Homes and businesses received orders to switch off power during mornings and afternoons. Factories operated on priority schedules. Civilian heating was sacrificed to keep war production running. Even though the war had ended, this demonstrated the grid's wartime achievement in stark relief. During 5 years of active warfare, with bombing, labor shortages, and transportation chaos, the grid never experienced system-wide failure. The 1947 crisis happened only after wartime discipline and priority allocation ended. The coal crisis revealed another critical aspect of grid management: spare capacity. Before the national grid, Britain's 600-plus independent electrical undertakings maintained an average of 80% spare capacity. This meant for every power station running, 4/5 of backup equipment sat idle. The capital waste was enormous. The interconnected grid reduced spare capacity to 15% by 1938. Because stations could back each other up through transmission lines, individual stations didn't need massive redundant equipment. This capital saving was calculated at 75% of the grid's construction cost. Building the grid cost approximately $27 million. The reduced spare capacity saved nearly $20 million in avoided power station construction. And those savings came before the war, demonstrated the grid's strategic value. The military understood this value clearly. Unused electricity in blacked-out London could supply northern factories. Southern stations could reinforce the Midlands when local stations were hit. Welsh generators could back up Bristol when needed. This flexibility wasn't just efficient, it was strategically essential. Compare Britain's electrical resilience to Germany's system. Germany had standardized electricity earlier than Britain, with regional utilities operating since the 1920s. But German electrical infrastructure lacked Britain's interconnected redundancy. When Allied bombers began targeting German industrial centers in 1943–1944, hitting power stations caused localized industrial collapse. Destroying a single power plant could black out entire factory complexes for weeks. The Schweinfurt ball-bearing factories, critical to German aircraft production, were vulnerable to electrical disruption. The Ruhr industrial region depended on concentrated power generation. Bombing raids in 1944 caused cascading failures because German grids couldn't reroute power as flexibly as Britain's system. German war production declined sharply in 1944, partly because Allied air campaigns destroyed electrical infrastructure faster than it could be repaired. Britain experienced the opposite trajectory. Despite German bombing from 1940–1941, British production increased every year. The numbers tell the story. In 1939, Britain produced 7,940 aircraft. In 1940, during the Blitz, production increased to 15,049 aircraft. In 1941, with bombing continuing, production reached 20,094 aircraft. In 1942, production hit 23,672 aircraft. By 1943, Britain was producing 26,263 aircraft annually. German aircraft production followed the opposite curve. In 1939, Germany produced approximately 8,295 aircraft. In 1940, 10,826 aircraft. In 1943, production peaked at 25,527 aircraft. But by 1944, production collapsed to around 40,000 for the year as Allied bombing destroyed German infrastructure, including electrical generation. The difference wasn't just bomb tonnage, It was infrastructure resilience. Britain's interconnected grid could absorb damage and continue operating. Germany's concentrated generation created single points of failure. British electrical engineers understood this advantage. They deliberately dispersed generating capacity. They built redundant transmission lines. They trained operators to manage the grid during emergencies. This wasn't accident, it was doctrine learned from World War I. During WWI, British munitions factories had faced catastrophic coal shortages in 1917–1918. Coal prices doubled. Generators failed. Production stalled. The lesson was clear. Electrical infrastructure was strategic infrastructure. The 1926 Electricity Supply Act explicitly recognized this. The Act's preamble noted that efficient electrical supply was essential for national security. The Central Electricity Board's mandate included ensuring reliable supply during emergencies. When war came in 1939, this foresight paid dividends. The human dimension of grid operations during wartime is often overlooked. Grid engineers and power station workers operated under immense psychological pressure. They knew their work directly determined whether soldiers had weapons, whether ships had armor, whether aircraft could fly. Richard Morrison, a grid engineer at East Grinstead Area Control, wrote to his sister in February 1941, "We received word that a convoy assembling at Portsmouth needed priority power for loading operations. Simultaneously, Vickers in Southampton required extra capacity for night shift work on bomber production. We had to throttle back civilian power to accommodate both. I calculated the load distribution for 6 hours. If I miscalculated, the grid could fail. That keeps you awake at night." Morrison survived the war and worked for the nationalised British Electricity Authority until his retirement in 1967. His wartime calculations, repeated thousands of times by dozens of engineers, kept the grid stable through 6 years of war. Another overlooked aspect: maintenance. Power stations require constant upkeep. Boilers need cleaning. Turbines need bearing replacement. Electrical switchgear needs inspection. Cooling systems need repair. During peacetime, stations could be taken offline for weeks for maintenance. During wartime, every station was critical. Maintenance had to be scheduled during minimal demand periods, usually pre-dawn hours. Repair crews worked overnight, completing tasks in 6 hours that normally took 6 days. George Whitfield, a maintenance engineer at Clarence Dock Power Station in Leeds, recalled a turbine bearing failure in March 1943. The bearing seized at 11 p.m. We had 4 hours until morning demand surge. Normal bearing replacement took 12 hours. We worked with emergency lighting, improvised tools, and sheer desperation. The turbine was back online at 4:47 a.m. I don't remember sleeping for 3 days afterward. This culture of urgent competence permeated grid operations. Failure wasn't an option. Delays weren't acceptable. The work simply had to be done. By 1943, the grid was handling electrical loads that would have seemed impossible in 1939. Peak demand had increased by approximately 40%. Generating capacity had increased by 180 megawatts through new construction. Efficiency improvements added equivalent capacity by optimizing existing stations. But the most important factor was operational excellence. Grid engineers could extract maximum output from stations originally designed for lower loads. They coordinated demand more efficiently. They minimized transmission losses. They balanced loads to prevent overloading individual generators. The result? Britain's war industry ran continuously. From 1939 to 1945, British factories produced 132,500 aircraft, 7,700 warships, 25,000 tanks, millions of artillery shells, billions of small arms rounds. Every single item required electrical power at multiple production stages. smelting metal for tank armor, operating stamping presses for aircraft components, running lathes for artillery shells, powering cranes in shipyards, illuminating factories for night shift work. Without stable electrical power, none of this production happens. Compare this to the counterfactual. If Britain had entered Dobbo Foods, with its pre-1926 fragmented electrical system, individual power station failures would have caused regional industrial blackouts. Bomb damage would have been catastrophic rather than manageable. Expanding production would have required building hundreds of new isolated power stations. Coordinating industrial production would have been impossible. Britain might have lost the war in 1940 simply through electrical inadequacy. The grid's success was so complete that it became invisible. Soldiers fighting in North Africa didn't think about the Manchester power stations supplying the factories that made their ammunition. RAF pilots over Germany didn't consider the Battersea turbines that kept the aircraft plants running. Sailors in the Atlantic didn't know that Welsh generators powered the shipyards building their destroyers. The grid was infrastructure. Infrastructure, by definition, fades into the background. It's only noticed when it fails, and Britain's grid never failed. VE Day, May 8, 1945. The war in Europe ended. For 2,073 days, Britain's electrical grid had sustained the nation's war effort. Through bombing, coal shortages, labor constraints, and unprecedented demand, the grid delivered power. The workers who made this possible received little recognition. No monuments commemorate grid engineers. No medals were struck for turbine operators. Power station workers weren't mentioned in victory speeches, but their contribution was absolute. 3 years later, the Electricity Act 1947 nationalized Britain's electrical supply industry. The Central Electricity Board was dissolved. The British Electricity Authority took control of generation and transmission. Local electricity boards managed distribution. Sir Archibald Page, who had led the CEB through the war as chairman from 1935 to 1944, retired. Harold Hobson, who served as chairman from 1944 to 1946, oversaw the transition. Sir Johnstone Wright, the chief engineer who had designed much of the grid's wartime expansion, became the final CEB chairman from 1947 to 1948 before nationalisation. These men and their teams had achieved something unprecedented. They had built the world's first synchronised national electrical grid. They had operated that grid through the most devastating conflict in human history. They had proven that infrastructure could win wars. The legacy extended beyond Britain. After W. Every major industrial nation studied Britain's national grid. The United States, despite having larger electrical capacity, lacked national integration. Regional grids operated independently, limiting resilience. Soviet planners examined British grid design when building their own electrical infrastructure. European nations rebuilt their post-war electrical systems using British interconnection principles. The national grid became the template for modern electrical infrastructure worldwide. Today, Britain's electrical grid is vastly more sophisticated. 400 kilovolt transmission lines replaced the original 132 kilovolt network. Nuclear power, natural gas, wind and solar replaced coal. Computer systems manage load balancing automatically. Interconnectors link Britain to continental Europe, but the fundamental principle remains unchanged. Interconnected resilience, redundant capacity, coordinated operation. The 1926 grid that saved Britain in 1940 established principles that define electrical infrastructure in the 21st century. In October 2024, Britain closed its last coal-fired power station, Ratcliffe-on-Soar in Nottinghamshire. This ended 142 years of coal generating electricity in Britain. The closure was symbolic. The infrastructure those coal stations built, the interconnected national grid, remains Britain's electrical foundation. That grid, forged in the 1930s and tested in the 1940s, represents a particular kind of achievement. It wasn't glamorous, it wasn't celebrated, it wasn't obvious, but it was essential. Britain's war was fought on visible battlefields, Spitfires in the sky over Britain, destroyers in the Atlantic, tanks in the North African desert, infantry landing on Normandy beaches, but it was also fought in generator halls, in control rooms, at turbine stations, along transmission lines, where engineers managed megawatts, where workers shoveled coal, where operators synchronized generators, where maintenance crews worked through air raids. This was Britain's hidden battlefield. The power plants that kept Britain's war industry alive weren't just supplying electricity, they were supplying capability. The capability to produce, the capability to fight, the capability to survive, the capability to win. When historians analyze Britain's survival in 1940, they focus on the Battle of Britain, Churchill's leadership, RAF fighter pilots, radar technology, the few who saved the many, all true, all essential, all celebrated. But underneath that visible heroism was invisible infrastructure. The grid that powered the factories that built the fighters, the stations that generated electricity for the radar installations, the transmission lines that kept the aircraft plants running, the engineers who ensured the power never failed. This was Britain's foundation, not the visible superstructure, but the hidden substructure that made everything else possible. In March 1941, an unnamed grid engineer wrote in the CEB internal newsletter, "The public sees the Spitfire. They don't see the 4,000 megawatt hours that went into building it. They see the factory. They don't see the transmission lines that power it. They see the lights staying on during the Blitz. They don't see the coal handlers, the turbine operators, the maintenance crews who made it happen. That's fine. Our job isn't visibility. Our job is reliability, and we will not fail." They didn't fail. For 6 years, through bombing and coal shortages and impossible demand, Britain's electrical grid delivered. Every day, every hour, every minute. The grid was more than infrastructure. It was national will made tangible, British determination converted into megawatts, the refusal to surrender expressed in synchronized generators. Let's examine the technical reality that made this possible. A coal-fired power station in 1940 was a symphony of precisely coordinated mechanical processes. Coal arrived by rail, typically 50 to 200 tons per day for a medium station. Mechanical conveyors transported coal to pulverizers that ground it to powder finer than talcum. This powder was blown into furnaces where it burned at temperatures exceeding 1,400 degrees Celsius. The heat converted water in boiler tubes to superheated steam at 400 to 600 psi. This steam entered turbines spinning at 3,000 revolutions per minute. The turbine drove a generator producing alternating current at precisely 50 Hz. Any deviation from 50 Hz created grid instability. Maintaining frequency required constant adjustment of steam pressure, which meant constant adjustment of coal feed rate. A single 40 megawatt turbine, like the one at Early, consumed approximately 150 tons of coal daily at full output. That's 1 ton of coal every 9.6 minutes, 24 hours a day. Coal handlers worked in brutal conditions. The coal dust was caustic, blackening skin and choking lungs. Summer temperatures near the furnaces exceeded 45 degrees Celsius. Winter shifts were barely better, with freezing cold alternating with furnace heat. Albert Jennings, a coal handler at Hackney Power Station, wrote to his wife in July 1942, "My hands are bleeding again from the coal. The dust gets into every crack in your skin. I cough black for hours after my shift, But every shovelful keeps one more light burning in Britain. I'll take bleeding hands over German occupation any day. Jennings died in 1944 from pneumoconiosis, coal workers' lung disease. He was 38 years old. He had worked 1,158 shifts without absence. The generators themselves were engineering marvels. A typical 1940s alternator weighed 80 to 120 tons. The rotor spun inside stator coils with clearances measured in millimeters. Bearing temperatures had to be monitored constantly. Overheating meant catastrophic failure. Cooling systems circulated thousands of gallons of water per hour. Generator operators monitored massive analog control panels. Voltage meters, frequency indicators, load gauges, temperature sensors, oil pressure monitors. These instruments had to be read and interpreted continuously. An experienced operator could hear problems before instruments registered them. A slight change in turbine pitch indicated bearing wear. Unusual vibration suggested rotor imbalance. Steam valve chattering meant pressure fluctuation. Margaret Hensley, one of the few women employed as a generator operator at Croydon Power Station, described the sensory experience in a 1943 letter. You don't just watch the instruments, you listen to the turbine. You feel the vibration through the floor. You smell the bearing oil. After 6 months, you know your turbine better than you know your own heartbeat. When something's wrong, you feel it in your bones before the meters show it. Hensley operated generator number 3 at Croydon for the entire war. Her turbine never failed unexpectedly. She logged 11,247 operational hours without unplanned shutdown. After the war, she trained male engineers on operational techniques. She retired in 1962 as senior generator supervisor. The grid control centers were equally sophisticated. Each regional control center had maps showing every power station, every major transmission line, every substation in their area. Colored lights indicated operational status. Green, operating normally. Yellow, reduced capacity. Red, offline. Flashing red, emergency. Control engineers had direct telephone lines to every station. They tracked real-time demand using electromechanical strip chart recorders. These devices drew continuous graphs of power consumption. Engineers could see demand rising and predict when additional capacity would be needed. During peak demand, typically 6 p.m. to 10 p.m., when factories ran evening shifts and domestic consumption spiked, control centers resembled military command posts. Engineers shouted updates across the room. Telephones rang constantly. Strip chart recorders showed demand climbing in real time. Decisions had to be made in seconds. James Crawford, a control engineer at Birmingham Area Control, recalled the evening of November 19, 1940. The Coventry raid was underway. We could see the glow in the sky. Coventry's demand dropped to almost nothing as the city evacuated. But Birmingham factories increased production to compensate. Our demand spiked by 35% in 20 minutes. We had to activate 3 reserve stations simultaneously. One engineer calculated load distribution. Another coordinated with surrounding areas. I managed the activation sequence. We brought 60 megawatts online in 18 minutes. If we'd been 30 seconds slower, Birmingham would have blacked out. The entire Midlands industrial base would have stopped. Crawford worked in grid control for 42 years. He calculated that during the war, he personally coordinated power delivery totaling over 2,000 gigawatt hours. That's enough electricity to build approximately 50,000 aircraft. The grid's technical challenge extended beyond generation and control. Transmission created its own problems. Electrical current flowing through transmission lines generates heat. This heat causes the lines to expand and sag. Too much sag and lines could short-circuit against trees or structures. but transmission lines had to carry maximum current during wartime peak demand. The solution was continuous monitoring and maintenance. Linesmen patrolled transmission routes, inspecting pylons, checking clearances, identifying damage. This work happened regardless of weather. Rain, snow, fog, darkness. Linesmen worked. During air raids, transmission lines were vulnerable. A bomb exploding near a pylon could sever lines without directly hitting them. Shrapnel could perforate conductor cables. Blast waves could snap insulator strings. Repair crews had to restore power under combat conditions. They worked in blackout darkness. They climbed pylons while bombers flew overhead. They repaired high-voltage equipment that could kill instantly if improperly handled. Walter Simmons, a linesman in the London area, described a repair in October 1940. A bomb had severed the main transmission line from Barking Power Station. The line was carrying 132,000 volts. We had to splice it in complete darkness because of the blackout. One mistake meant electrocution. We worked by touch, wearing insulated gloves, communicating with hand signals because we couldn't use lights. Took us 4 hours. The line was energized at 3:47 a.m. We'd restored 40 megawatts of capacity. I was so exhausted I slept on the ground beside the pylon until dawn. Simmons survived the war and worked as a master linesman until 1958. He trained over 200 linesmen in high-voltage repair techniques. His wartime procedures became standard practice for British electrical utilities. The comparison between British and German electrical infrastructure reveals why Britain's system succeeded. Germany had more generating capacity than Britain in 1939. German heavy industry, steel mills, chemical plants, aircraft factories, consumed enormous electricity. The Ruhr industrial region alone had generating capacity exceeding the entire output of London's power stations. But German electrical infrastructure was regionally concentrated. The Ruhr Valley had massive generating capacity because heavy industry concentrated there. Siemens factories in Berlin had dedicated power stations. IG Farben chemical plants had their own generating facilities. This created efficiency in peacetime, but vulnerability in wartime. When Allied bombers began targeting the Ruhr in 1943, they discovered that destroying a few key power stations paralyzed entire industrial complexes. The RAF raid on the Möhne and Edda dams in May 1943, Operation Chastise, the Dambusters raid, wasn't just about flooding. It was about electricity. The dams powered hydroelectric stations, supplying the Ruhr's steel mills and armament factories. Destroying the dams knocked out those hydroelectric stations. Steel production in the Ruhr dropped 40% in the following month. Britain's distributed grid had no equivalent vulnerability. Destroying Battersea Power Station wouldn't cripple London because power could be imported from surrounding regions. Destroying Birmingham stations wouldn't stop Midlands production because generators in Wales and the north could compensate. The interconnected redundancy that seemed inefficient in peacetime became decisive in wartime. German war production statistics demonstrate this impact. In 1943, Germany produced 25,527 aircraft. In 1944, after sustained Allied bombing of electrical infrastructure, production was approximately 40,000 aircraft for the entire year. But monthly production collapsed from peaks of over 3,500 aircraft per month to under 2,000 by December 1944. British production showed the opposite trend. In 1943, Britain produced 26,263 aircraft. In 1944, production was 26,461 aircraft. Steady, consistent, reliable. The difference was electrical infrastructure resilience. The human cost of maintaining Britain's electrical grid extended beyond the workers already mentioned. Families sacrificed. Communities adapted. An entire generation lived with the consequences of prioritizing industrial power over domestic comfort. During the coldest months of winter, domestic heating was restricted to conserve coal for power stations. Homes were kept at temperatures barely above freezing. Children attended school in coats. Elderly citizens died from hypothermia in numbers that would be considered scandalous today. But this sacrifice was calculated. Every ton of coal burned in domestic fireplaces was a ton not available for power stations. Every kilowatt-hour used for home heating was electricity not available for munitions factories. The British public understood this calculus. They accepted it. They endured it. Mary Patterson, a Birmingham housewife, wrote in her diary in January 1942, "The house is so cold, we can see our breath indoors. The children sleep in every piece of clothing they own. But I pass the factory every day and see the lights burning. I know our cold house means warm factories. Our discomfort means production continues. I'll bear any hardship if it means defeating Hitler." This attitude pervaded British society during the war. Not mindless patriotism, calculated sacrifice with clear purpose. The electrical grid embodied this principle. Maximum output for war production, minimum consumption for civilian comfort. Total mobilization of national resources toward a single goal. By late 1944, Britain's electrical system was operating at capacity that would have seemed impossible in 1939. Peak demand had increased from approximately 3,500 megawatts in 1939 to over 4,900 megawatts in 1944. That's a 40% increase, while simultaneously managing bomb damage, coal shortages, and labor constraints. How was this achieved? First, stations operated beyond designed capacity. A turbine rated for 30 megawatts might be pushed to 33 megawatts by increasing steam pressure and accepting accelerated wear. This shortened equipment lifespan but maximized immediate output. Wartime necessity overrode peacetime caution. Engineers understood the trade-offs precisely. A turbine designed for 20-year operational life might last only 12 years when consistently overdriven. But Britain needed power now, not in 20 years. The calculation was ruthless but necessary. Sacrifice future capacity for present output. Replace equipment after the war. Survive first, optimize later. This philosophy extended to every component. Boilers operated at pressures 10 to 15% above design specifications. Generators ran at temperatures that triggered warning indicators. Cooling systems were pushed to thermal limits. Electrical switchgear handled loads beyond rated capacity. Safety margins built into peacetime equipment became wartime operational ranges. The technical specifications of this over-operation are illuminating. Consider Fulham Power Station in London. Station A, built in 1901, had an original rated capacity of 12 megawatts. By 1943, engineers were extracting 15.5 megawatts regularly. That's 29% beyond design capacity. How? They increased boiler pressure from 250 psi to 285 psi. They ran turbines at 3,150 RPM instead of the designed 3,000 RPM. They accepted bearing temperatures 40 degrees higher than peacetime maximums. They reduced maintenance intervals but increased inspection frequency. The result, more power output, but equipment failures increased by approximately 35%. Engineers calculated that even with increased failures, total output exceeded what cautious operation would achieve. They were trading reliability for capacity. In wartime, that trade made sense. Every power station made similar calculations. Multiply these incremental gains across 171 stations and the additional capacity becomes substantial. Approximately 350 megawatts of extra capacity came from overdriving existing equipment. That's equivalent to building 8 new 40-megawatt stations. without spending money on construction, without consuming steel needed for tanks, without diverting labor to building projects. Pure operational excellence. Second, maintenance schedules were ruthlessly optimized. Stations that normally underwent annual 2-week shutdowns for major maintenance instead operated for 18 months before shutdown. When maintenance did occur, it happened in 72-hour blitzes instead of leisurely 2-week overhauls. Crews worked in shifts around the clock. Parts were prefabricated. Every minute of downtime was planned to the second. The logistics of wartime power station maintenance were extraordinary. A typical major maintenance involved shutting down the turbine and draining steam systems, disassembling turbine casings to access rotor bearings, inspecting and replacing worn bearings, seals and gaskets, cleaning boiler tubes encrusted with coal ash and scale, testing electrical insulation on generator windings, calibrating control systems and safety mechanisms, reassembling everything and conducting operational tests. In peacetime, this process took 14 days. In wartime, maintenance crews completed it in 72 hours. Henry Wallace, a maintenance supervisor at Barking Power Station, explained the technique. We prefabricated every replacement part. We rehearsed the entire shutdown sequence. We had 3 crews working in rotation. The turbine stopped at midnight Sunday. By 6 a.m. Monday, we had it disassembled. Bearing replacement happened Monday afternoon. Tuesday was boiler work and electrical testing. Wednesday morning, reassembly. Wednesday evening, operational tests. Thursday at 1 a.m., back online. 73 hours, start to finish. We did this every 16 months for the entire war. Wallace and his crews performed 11 such maintenance operations during the war. 0 failures, 0 delays, 0 compromises on safety or quality. This level of precision maintenance, replicated across every power station, kept the grid running at capacity that should have triggered catastrophic equipment failures. But failures were managed, not prevented. When equipment did fail, replacement was rapid. The Central Electricity Board maintained strategic reserves of critical components, spare turbine rotors, replacement generator stators, boiler tubes, electrical switchgear, pumps, valves, and control mechanisms. These reserves were positioned strategically across regions. When Birmingham's Neshalls Power Station suffered a turbine failure in June 1942, a replacement rotor arrived from Manchester within 8 hours. Installation took 36 hours. The station was back online before its absence significantly impacted grid capacity. Without these strategic reserves and rapid response protocols, each equipment failure would have meant weeks or months of reduced capacity. The grid would have slowly degraded through attrition. By 1944, Britain's electrical capacity might have dropped below critical thresholds. Production would have stalled. The war effort would have faltered. Instead, Britain's electrical capacity increased every year of the war. The system didn't just survive, it strengthened. Third, efficiency improvements extracted more power from existing coal. Boiler operators learned to adjust air-fuel mixtures for maximum heat transfer. Turbine operators optimized steam pressure for peak efficiency. Transmission engineers reduced line losses by carefully managing voltage levels. The technical details of these improvements deserve examination. Coal combustion efficiency depends on precise air-fuel ratios. Too much air cools the furnace, reducing steam generation. Too little air causes incomplete combustion, wasting coal. The optimal ratio varies with coal quality, moisture content, and furnace conditions. Experienced boiler operators could achieve combustion efficiency of 85 to 87%. Inexperienced operators might only achieve 75 to 78%. That 10% difference means 10% more coal required for the same power output. Or conversely, 10% more power from the same coal. During the war, the CEB established training programs for boiler operators. Experienced operators taught efficiency techniques. The average combustion efficiency across the grid increased from 79% in 1939 to 84% by 1943. That 5% improvement, multiplied across millions of tons of coal, generated additional capacity equivalent to approximately 200 megawatts. Free capacity. From better training and operational excellence, transmission efficiency improved similarly. Electrical current flowing through copper conductors generates heat due to resistance. This heat represents wasted energy, power lost between generation and consumption. Transmission losses in Britain's grid averaged approximately 7.5% in 1939. Engineers reduced losses through better voltage management. Higher voltage reduces current for the same power transmission. Lower current means less resistive heating. Less heating means less loss. By carefully managing voltage levels, grid engineers reduced transmission losses to 6.2% by 1944. That 1.3% improvement sounds trivial. But with 4,900 megawatts of peak demand, 1.3% equals 64 megawatts. That's 1.5 large power stations worth of capacity, created by mathematical optimization of voltage levels. These incremental improvements, multiplied across 171 power stations, added up to substantial additional capacity without building new infrastructure. Fourth, demand management became sophisticated. Factories were encouraged to shift production to off-peak hours when possible. Non-essential industrial processes were scheduled for times when grid capacity was less constrained. The grid evolved from simply supplying power on demand to actively managing when demand occurred. This represented a fundamental change in how electrical grids operated. Before the war, utilities responded to demand. During the war, utilities influenced demand timing. The Ministry of Supply coordinated with the CEB to create production schedules that matched grid capacity. Factories producing non-urgent items operated during off-peak hours. Critical munitions plants received priority during peak demand. Heavy industrial processes like steel smelting were scheduled for nighttime when domestic demand was lower. This required unprecedented cooperation between industry and government. Factory managers had to coordinate production schedules with grid operators. Supply ministries had to prioritize which factories received power during peak demand. Workers had to accept shift changes based on electrical availability rather than convenience. It worked because everyone understood the stakes. The Lancashire textile mills provide a specific example. Before the war, mills operated primarily during daylight hours, matching worker preferences and traditional schedules. This created peak demand during daytime that strained grid capacity. In 1941, the Ministry of Supply negotiated with mill owners to shift 30% of production to nighttime. Workers received wage incentives for night shifts. The grid gained 180 megawatts of daytime capacity that could be allocated to munitions and aircraft factories. Textile production didn't decrease, it simply happened at different times. This demand shifting, replicated across multiple industries, effectively created capacity without building generators. The mathematical efficiency of this approach was remarkable. Consider a grid with 4,000 megawatts generating capacity. If demand peaks at 3,900 megawatts, the grid operates at 97.5% capacity with minimal reserve. By shifting just 200 megawatts of demand to off-peak hours, peak demand drops to 3,700 megawatts. The grid now operates at 92.5% capacity with 300 megawatts reserve. That reserve provides cushion for unexpected demand or generator failures. This buffering capacity proved critical during crisis moments. When Coventry was bombed in November 1940, Birmingham factories increased output to compensate. The available reserve capacity allowed Birmingham to accept the additional load. Without demand management creating that reserve, Birmingham couldn't have responded. Coventry's production would have been lost permanently. The post-war assessment of Britain's wartime electrical performance is remarkable. In 1946, a government commission investigating industrial production during the war concluded the electrical supply industry's success in meeting unprecedented demand under combat conditions represents one of the most significant, yet least recognized contributions to victory. Without the national grid's resilience and the dedication of electrical workers, British war production would have been impossible. The grid's wartime performance vindicated every penny spent on its construction. That assessment is not hyperbole. Consider the counterfactual scenarios. Scenario 1. Britain enters WTOPUD with the pre-1926 fragmented electrical system. Result: the first bombing raid that destroys a power station blacks out the surrounding area indefinitely. Aircraft production stops. Tank manufacturing halts. Ammunition filling ceases. Britain sues for peace by late 1940. Scenario 2. Britain builds the national grid, but coal shortages cripple generation. Result: factories operate at 60% capacity. Aircraft production drops by 40%. The RAF lacks sufficient fighters during the Battle of Britain. Britain loses air superiority. Operation Sea Lion becomes feasible. Britain invaded by spring 1941. Scenario 3. Britain's grid operates but lacks skilled operators to manage wartime demand. Result: cascading blackouts occur regularly. Production is inconsistent. Quality control suffers. Aircraft crash due to substandard components. Munitions fail in combat. British forces lose confidence in their equipment. Morale collapses. None of these scenarios occurred because Britain's electrical infrastructure succeeded completely. The specific factories dependent on grid power demonstrate the scale of industrial mobilization. The Vickers-Armstrong Supermarine facility at Castle Bromwich produced 11,694 Spitfires during the war. Every aircraft required approximately 15,000 man-hours of labor. Most of that labor involved electrically powered tools. Drilling rigs, rivet guns, hydraulic presses, welding equipment. The factory consumed 8.5 megawatts during peak production. Without uninterrupted power, Spitfire production stops. The AV Row factory at Woodford produced 3,629 Lancaster bombers. Each Lancaster required 55,000 man-hours to build. The factory operated 3 shifts, 24 hours daily. Peak electrical consumption, 12 megawatts. A 4-hour blackout meant production delays measured in days because assembly sequences couldn't be interrupted without scrapping partially completed components. Royal Ordnance Factory Chorley in Lancashire filled 3.5 million artillery shells during the war. Shell filling required precise temperature control of explosive compounds. The process consumed 6.2 megawatts continuously. Power fluctuations could cause explosive instability. Voltage variations exceeding 2% triggered automatic production shutdown for safety. Grid stability wasn't convenience. It was survival. These 3 facilities alone consumed 26.7 megawatts during peak operation. That's 2/3 of the total capacity added by early power station. Multiply across hundreds of factories, and the total demand becomes staggering. The grid delivered. Every day, every hour, every second. The human cost of maintaining Britain's electrical grid extended beyond the workers already mentioned. Families sacrificed, communities adapted, An entire generation lived with the consequences of prioritizing industrial power over domestic comfort. During the coldest months of winter, domestic heating was restricted to conserve coal for power stations. Homes were kept at temperatures barely above freezing. Children attended school in coats. Elderly citizens died from hypothermia in numbers that would be considered scandalous today. But this sacrifice was calculated. Every ton of coal burned in domestic fireplaces was a ton not available for power stations. Every kilowatt-hour used for home heating was electricity not available for munitions factories. The British public understood this calculus. They accepted it. They endured it. Mary Patterson, a Birmingham housewife, wrote in her diary in January 1942, "The house is so cold we can see our breath indoors. The children sleep in every piece of clothing they own. But I pass the factory every day and see the lights burning. I know our cold house means warm factories. Our discomfort means production continues. I'll bear any hardship if it means defeating Hitler." This attitude pervaded British society during the war. Not mindless patriotism, calculated sacrifice with clear purpose. The electrical grid embodied this principle: maximum output for war production, minimum consumption for civilian comfort, total mobilization of national resources toward a single goal. By late 1944, Britain's electrical system was operating at capacity that would have seemed impossible in 1939. Peak demand had increased from approximately 3,500 megawatts in 1939 to over 4,900 megawatts in 1944. That's a 40% increase, while simultaneously managing bomb damage, coal shortages, and labor constraints. How was this achieved? Germany tried to bomb Britain into submission. They hit the docks, the factories, the cities, the power stations. They expected industrial collapse. They expected capitulation. They expected Britain to fail. Britain's electrical grid was the silent answer. Not with words, not with defiance. With uninterrupted power delivery, the factories kept running, the lights stayed on, the grid held, and Britain won. In the final analysis, Britain's victory in World War II rested on three foundations: military valor, political leadership, industrial capacity. The third foundation depended entirely on the first two letters of electricity. The power plants that kept Britain's war industry alive weren't merely supplying electricity. They were supplying resistance. The resistance of a free people who refused to surrender. The resistance of workers who showed up despite bombs. The resistance of engineers who solved impossible problems. The resistance of a system that refused to fail. This resistance, measured in kilowatt hours and transmitted through high-voltage lines, was as decisive as any battle. Today, when you flip a light switch in Britain, electricity flows instantly. You don't think about the grid. You don't consider the transmission network. You don't recall the power stations. But that instant, reliable power is the legacy of the wartime generation. The engineers who built the grid, the workers who operated it, the families who sacrificed for it, the nation that depended on it. They created something unprecedented: a synchronized national electrical network that could withstand the greatest military assault in history. A system so resilient it never failed during 6 years of total war. An infrastructure so effective it became the global model for electrical distribution. This was Britain's hidden weapon, not glamorous, not celebrated, not obvious, but absolutely, completely, utterly essential. The power plants kept Britain fighting. The grid kept Britain producing. The electrical workers kept Britain alive. And in doing so, they helped keep the world free. 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 The world free.